All right, let's get right into it. We're going to tackle a huge question today. How does a machine actually learn? And spoiler alert, it's not magic. It's really just a fascinating process of trial and error, and it's all guided by some surprisingly simple math. So let's break it all down.
I mean, we hear about AI learning all the time, right? But what does that even mean? How does a piece of code, just a bunch of software, go from knowing literally nothing to suddenly being able to make predictions or recognize your face in a photo or even drive a car? Well, the secret, and this is really the core of the whole thing, is that a machine learns by scoring its own mistakes. It's kind of like a game. It gets told exactly how wrong it is, and its only goal is to make that wrongness score as low as it can possibly get. It's just this constant loop of feedback and tiny improvements. Okay, so let's really dive into that idea. Because to get how an AI learns from its mistakes, you first got to understand what its goal even is.
So just picture a machine learning algorithm as this system that basically just eats up tons and tons of examples. Every single example has some input data, we'll just call that X, and it also has the correct answer, which we'll call Y. So the algorithm's entire job is to look at all these X's and Y's and come up with a rule, a hypothesis, which we label H, that can take any new X it's never seen before and guess the right Y.
Okay, so the machine comes up with a hypothesis, a rule. But how do we know if it's any good? I mean, is it a great rule or a terrible one? Well, we need a way to score it. And that brings us to this really critical idea, the penalty score. Right. In the world of machine learning, this is officially called a loss function. And all it is really is a math formula that calculates the cost or the penalty for a prediction being wrong. It just measures that gap between what the model guessed and what the right answer actually was. The golf analogy is absolutely perfect here. You want the lowest score possible. A score of 0? That's a hole-in-one, a perfect prediction.
But here's the thing. We don't just care about getting one prediction right. That's easy. We need a hypothesis that works well across all of our data. So what we do is we calculate the loss for every single data point, and then we just take the average. That final average score, that's what tells us how good our hypothesis is overall.
I know. This is all still a little bit abstract. So let's make it super concrete. Let's do a simple case study I'm calling the mango test. Our mission, should we choose to accept it, is to build a model that can tell us if a mango is good or bad.
And for a simple problem like this, we can use the absolute simplest loss function there is, the 0-1 loss. And it's exactly what it sounds like. If the model gets it right, the loss is 0. If it gets it wrong, the loss is 1. That's it. Simple as that.
Let's walk through this. Look at Mango 1. The model predicted good, and the actual truth was good, perfect, so the loss is 0. But then look at Mango 2. The model said good, but oops, it was actually bad. That's a mistake, so we give it a penalty score of 1. Same thing happens with Mango 3. And then Mango 4, another correct guess, so the loss is back to 0.
Okay, so what happens when we have two competing models? Let's call them H1 and H2. Which one's better? Well, we just look at the average loss. H1, our first model, has an average loss of 0.5. It got half of them wrong. But look at H2. It got every single one right, a perfect average loss of 0. So which one do we pick? It's a no-brainer. We pick H2 because the entire goal of this whole learning process is to find the hypothesis with the absolute lowest loss.
That seems pretty straightforward for a simple yes or no question, right? But the real world is a lot messier. That 0-1 loss we just used, it treats every single mistake as equally bad. But is that always how it works?
Yeah. Think about it like this. What if a mistake isn't just wrong, but it's really wrong? Imagine you're predicting house prices. Being off by, say, $1,000, okay, not great, but it's one thing. Being off by $100,000? That's a way bigger deal. We need a loss function that gets that understands the size of the mistake.
So here are two really popular ways to handle that. Over on the left, you've got L1 loss, or mean absolute error. See that V shape? The penalty just grows in a straight line. If your error gets twice as big, the penalty gets twice as big. Pretty simple. But now look at the one on the right. That's L2 loss, or mean squared error. And that U shape is the whole story. Because it squares the error, the penalty doesn't just grow, it accelerates. A mistake of 2 isn't twice as bad as a mistake of 1, it's 4 times as bad. This one really punishes big mistakes.
Let's actually put some numbers on this to see what I mean. So let's say we have a bunch of small, reasonable errors. The mean absolute error, the MAE, comes out to 1.0. The mean squared error, MSE, is a little higher at 1.5. they're in the same ballpark, no big deal.
But now, watch this. What happens if we throw in one outlier? Just a single, huge mistake, an error of 15. The MAE, it goes up to 3.8. Okay, it's bigger. But the MSE, it explodes to 46.2. It goes through the roof. That one huge mistake completely takes over the entire score. And this is why picking the right loss function is so important. It literally tells your model what kind of mistakes it should be terrified of making.
Okay, so we've got a way to score a model, to tell it how bad it is. The next logical question is, how do we use that score to make it better? Well, this process, my friends, is what we call training. Let's go to a classic example, linear regression. You've seen this before. We've got a scatter plot of data points, and our whole job is to draw the one straight line that best fits that data. And when we say best fit, what we really mean is the line with the lowest possible loss. We're just trying to wiggle that line around until the total distance from all those points to the line is as tiny as we can make it.
So how does a computer actually find that perfect line? Well, it uses an algorithm called gradient descent. And honestly, the best way to think about it is this. Imagine you were standing on a mountainside, but it's super foggy. You want to get to the lowest point in the valley, but you can't see it. What do? Well, you can feel the ground at your feet, right? You can tell which way is downhill. So you take a little step in that direction. Then you stop, feel the ground again, find the new downhill, and take another step. You just do that over and over.
That's exactly what the computer is doing. It starts with just a totally random line. Then it calculates its loss score. How bad is it? Step 3, it uses a little bit of calculus, that's the gradient part, to figure out which way is downhill. Basically, how should I change the line to make the score a little bit better? Then it just nudges the line's parameters a tiny bit in that direction. And then it just repeats over and over and over again, millions of times, until it gets to a point where it just can't go any lower. That whole cycle, that is what training a model is.
Okay, so let's zoom out for a second and tie this all together, because it's honestly kind of mind-blowing that this one simple idea, just measuring your mistakes and trying to make that number smaller, is the engine that powers so much of modern AI.
If there's one thing you take away from this, it's this. Minimizing a loss function isn't just a part of machine learning, it is the learning. That's the whole game. We, the humans, define what good looks like by creating a scoring system. And then we just set the machine loose to find the best possible way to get the lowest score.
And the single idea, defining a goal as a number to be minimized, is behind almost everything you see. It doesn't matter if we're talking about recognizing your face, translating from Spanish to English, or recommending the next movie you should watch. The principle is exactly the same. We frame the problem as this vast, complex landscape, and the AI's only job is to go find the lowest point in the valley. It's such a simple concept, but it unlocks all this incredible complexity. And that leads to a really interesting final thought. If we can teach a machine to minimize the error in a simple prediction, what else could we teach it to minimize? Think about it. What if the number we're trying to shrink isn't just about getting a prediction right, but something bigger? What if we could teach an AI to minimize energy waste in a power grid, or minimize traffic jams in a city, or maybe even minimize the time it takes to discover a life-saving drug? Once you realize you can define almost any goal as a number to be minimized, well, the possibilities get pretty excited.